Well, I guess they don't really need the dark matter introduction. So this is a good moment to start. So yes, in the 1600s, theorists had proved that there are only 6 planets in the solar system. This is, of course, Kepler's model in terms of platonic solids. We actually have an original edition of this book in our library. So I wasn't aware before that we had a rare manuscript library, but we do. Nothing. Oh wait, it's back to full screen. Yeah. Okay. Yeah. Well, nothing kills your theory that there are 6 planets better than the discovery of the 7th one, which happened by chance, not in Kepler's own lifetime, but it could have happened in his lifetime. It's a little mysterious why Uranus wasn't discovered earlier, because it is visible without telescopes if you look very carefully, and the skies are good, which they used to be. But perhaps the more dramatic story, which everyone knows, is the discovery of planet 8, Neptune, which was predicted. And this is a little bit like the dark matter paradigm, because Neptune was discovered because of the perturbations it produced on the known planets, particularly Uranus, which wasn't following the Newtonian orbit. And I guess if you take the point of view that you believe in Newtonian gravity, then you can infer the existence of this planet from the perturbations. And they predicted its exact location in the sky, and it was found the same night. So that was a very dramatic success of Newtonian gravity. And of course, that immediately sparked off further searches for other planets, again, based on the same idea that you look for anomalies in the orbits of the planets that you can see. And then from those anomalies, you try to infer where this other planet might be. And that has never been successful. In the entire history of science, we've only discovered 2 planets. We've discovered thousands of planets around other stars, but we've discovered only 2 planets in our solar system, which is Uranus and Neptune, that weren't, already advertising themselves to the unaided eye. So there've been about 30 or so failures in looking for extra planets, but I'll just mention the 2 most prominent ones. There were some anomalies in the orbit of Mercury, discovered in the 1850s, and by 1900 they were really quite pronounced because of the precision with which these things were measured then. And this led to the prediction of a planet named Vulcan, a name that was later co-opted by Star Trek. But as you know, that planet was never found, because when you're in the inner solar system, the sun's gravity is relatively strong. And so post-Newtonian corrections from general relativity actually do matter. And that was the explanation. That was Einstein's big success. So that's an example where orbital anomalies led to the discovery of a modified law of gravity rather than of a new planet. And then there were also anomalies in the orbit of Uranus and Neptune, which led to a big search for an outer planet. And over there, of course, you don't expect general relativity to come to the rescue, because gravitational fields are very weak in the outer solar system. The sun's field is very weak in the outer solar system. But in this case, it turned out that the data were faulty, that as better data were accumulated, there were no anomalies in the orbits of Uranus and Neptune. The discovery of Pluto was a kind of fluke. It was found during the search for, it used to be called Planet X, this planet that was perturbing Uranus and Neptune. And when Pluto was found, of course, everybody thought it was Planet X, but it turned out soon enough that it's much too small. And in fact, it's probably much too small to be considered a planet even. What Pluto really is it's an early member of what's called the Kuiper belt. This is a bunch of icy chunks of ice that you find in the outer solar system beyond the orbit of Neptune. And this is just an artist's rendition, but I should probably have gotten a real photograph for this talk, because we've had a couple of flybys and it's pretty dramatic that you can actually see these icy chunks up close. At this point, thousands of Kuiper belt objects are known. Pluto was discovered in the 1930s. The second Kuiper belt object was discovered in the 1990s. And by now, like I said, thousands of them are known. And so astronomers have a kind of taxonomy for them. They come in 4 families. Some of them are locked into resonance with Neptune. So their orbital period is twice that of Neptune, or 1.5 times that of Neptune, which is a 3:2 resonance. This is called the resonant Kuiper belt. And then you have all these objects that are somewhere in between those two orbits, the 3:2 and the 2:1 resonance. This is where the majority of them, the known ones, lie. And this is called the classical Kuiper belt. But more interesting Kuiper belt objects are the ones that are called the scattered disk. So these are objects which lie entirely outside the orbit of Neptune. At the closest approach, they might come in, maybe 30 or 40 astronomical units. The distance of Neptune from the sun is 30 astronomical units. But then they swoop out to hundreds or maybe even thousands of astronomical units. So they have eccentric orbits, and they are fundamentally creatures of the outer solar system, the trans-Neptunian part of the solar system. You also have these objects called centaurs, which, and I should say that there's a subfamily of the scattered disk that I'm especially interested in, that I'll be talking mostly about. You also have objects called centaurs, which tend to both swoop very far out, but they also come into the inner solar system. So they have extremely complicated orbits because they're perturbed by everything under the sun. They're essentially chaotic orbits. They're also quite interesting, but they're complicated. So we're going to steer clear of those for now. And then I guess, as I said before, the Kuiper belt was discovered mostly starting with the 1990s. And the interesting thing I want to draw your attention to is this object called Sedna, which was discovered in the early 2000s. What's interesting about Sedna is that it never comes very close even to Neptune. So its innermost approach is, I forget the exact number, but I have a tabulation somewhere. It's about 50 astronomical units, and then it swoops out to hundreds. So it's not very strongly affected by the inner solar system. And so that's significant for us as well as for Planet 9. And the thing about Sedna is, if it was the only object of its kind, it wouldn't be so interesting. But since the last 5 years, additional objects like Sedna have been discovered, and those are the ones we want to focus on. Okay, so what's interesting about this Sedna family is, and you can see this in a plot from a review article about Planet 9. What you can see about them, and I think I'd like you to focus on those purple ellipses for now, because those are the best examples of the Sedna family. What you see is that these orbits are aligned. They're not all absolutely perfectly lined up, but the preponderance of them, they all point in a certain direction to the top right corner of this plot. What's shown over there is what's called the apsidal vector. So that's a line drawn from the sun to the point of closest approach to the perihelion. And you just make it a unit vector or the same length for all of them for clarity. And you can see that these apsidal vectors are all clustered together. So this is the kind of thing that is puzzling. I mean, there's no reason why it should be clustered in that way. You'd expect it to be random. And if you look at the things that aren't in the Sedna family, it is random, this alignment, the orientation of the orbits. And so this is the kind of thing that's used as evidence that suggested the existence of Planet 9. Here's some more.
Sorry, Harsh, could you say again, when you say the Sedna family versus not the Sedna family, what is the distinction?
So they don't. They have eccentric orbits. Their closest approach is 50 or 60 or more astronomical units. So they don't come close to Neptune. Most of the scattered disk objects, their closest approach is about 30 some astronomical units. So they swoop past Neptune, and so they're gravitationally perturbed by it as well as by the inner solar system. But the Sedna family stays far enough away that they aren't affected by the solar system.
I see.
Inner solar system.
And
yeah.
and were the green ellipses on the previous slide
including
those other elements, or?
Yeah, they're somewhat more marginal examples of the Sedna family, because if you can just and we don't do this kind of thing yet, but these guys they've done orbit dynamics on these. And they find these purple orbits are really very perfect ellipses if you work with the 8-planet model, and highly stable. But the ones that are in other colors do feel some perturbations from the inner planets, and those orbits tend to drift. Okay. So they're not very good probes of an extra planet, because they're already influenced by the inner planets, or of modified gravity for that matter. So we really like the purple ones. But you can beef up your data by saying that those green ones are also kind of out there. And then you can say, 14 objects or 20 objects rather than just 6. Okay, so here's another example. So I guess I'll talk a little bit more about this, but orbits are characterized by 5 fundamental parameters. There's the semimajor axis and the eccentricity of the orbit, which describe its shape and size. And then you have these 3 Euler angles, which describe how that ellipse is oriented in space. And if you look at one of these Euler angles, omega, that describes the orientation, as a function of the distance of the Kuiper belt object. So they've just looked at hundreds of Kuiper belt objects over here. You see that this parameter omega is fairly randomly distributed when you're in the inner solar system at 30 to 100 astronomical units for your major axis. But when you go far out, perhaps to the Sedna family, which tend to have very large semi-major axes, you see that this omega parameter tends to be 360 degrees. There's a clustering in omega. So it's from clustering like this, orbital alignments and things like that. One way to explain these things is that there is a 9th planet in the solar system, which the best fit to these data are that it's 500 astronomical units from the sun and about 5 to 10 Earth masses, which is not quite on the same scale as the giant planets, but it's certainly substantially bigger than the Earth. So that's the Planet 9 hypothesis, that these data can be explained by the existence of another planet. So now finally I can get to our work, and I'll explain the title of this section and of our talk in just a moment. So I want to tell you a little bit about MOND gravity now. And for that, it might be helpful to back up and talk about Newtonian gravity first. So this is not how you learn Newton's laws in Physics 101, but you can think of it as a field theory, just like Maxwell's, just like electrostatics. You have the basic field is the acceleration due to gravity, which is a vector, and just like because mass produces gravity, it turns out the divergence of G is related to the mass density. And you can have fun using the electrostatic analogy and trying to figure out the analogy between Newton's law and Coulomb's law and figuring out why there's a minus sign there and where the 4 pi G comes from and so on. And also the gravitational field is curl-free, just like in electrostatics. And then to complete the field description of Newtonian gravity, you have to give the force law, which is the analog of F is equal to QE in electrostatics, and in gravity it's mg. So that's Newton's laws formulated as a field theory. And now I can describe to you quasi-linear MOND. So there's 2 versions of MOND. There's the original version, which is introduced by Bekenstein and Milgram. And then there's quasi-linear MOND, which is slightly simpler to work with, and that's the one I'll talk about. But you can show that they give essentially the same results, both theories. So here's how a quasi-linear MOND works as a recipe. Suppose you've got some mass distribution. The first thing you should do is figure out the Newtonian gravitational field it produces. But this Newtonian gravitational field, it's got nothing to do with reality. That's not what a test mass will experience, or that's not the acceleration a test mass will have. What you do with this Newtonian field is that you calculate something called the Pristine Field, and that's a very nonlinear function of the Newtonian field. It's the Newtonian field multiplied by this modulation factor. There's this thing called nu, which is called the interpolating function. And it's a function of the magnitude of the Newtonian field at that point, divided by A naught, which is a fundamental new constant of nature, if MOND is in fact the correct theory of gravity. This acceleration can be fit to galaxy rotation data, and it's about 10 to the minus 10 meters per second squared. So it's a very small acceleration. I'll say a little bit more about what the interpolating function is. Yeah, let me hold off on that for a second. But basically it's designed so that if the gravitational field is strong, then the interpolating function is 1. So the pristine field is equal to the Newtonian field. But if G is small compared to A naught, then the pristine field is quite different from the Newtonian field. That's what this modulation factor achieves. Okay, but this pristine field is also not the physical field. It's just an intermediate step in the calculation. The physical field is what I call GQ, the quasi-linear field, and that's the curl-free part of the pristine field. Because the Newtonian field is, of course, curl-free, but when you modulate it, it stops being curl-free, and then you have to extract the curl-free part. And GQ is the physical gravitational field. It's what test masses will respond to. So you can see that this is actually very easy to, this is a theory which is relatively easy to compute with, because calculating the Newtonian field is just a matter of solving the Poisson equation. You have to put it through a nonlinear function, and then you're back to solving a Poisson equation, because GQ has the same divergence as GP, and it's curl-free. So you're basically solving a Poisson-like equation again. Okay, so now let me say exactly what the interpolating function is. You want it to be 1 when the argument is big, so that for strong fields, you recover Newtonian gravity. But for small fields, for small arguments, you want it to go like 1 over square root of x. And this is what produces the flat rotation curves, as we'll see in a moment, to choose 1 over square root of x. That's inexorable. It comes out of the flat rotation curves. What happens in between? Well, that's not actually very well constrained by the data. And so that's something that ultimately, I guess, experiments or some more fundamental relativistic formulation of MOND will ultimately give us what it is for intermediate x. But the galaxy rotation data can be fit to this form, which is quite often used in fitting galaxy in things like the radial acceleration relation. So that's what we'll work with. And this interpolating function is relatively abrupt. It goes quite quickly from being 1 to being 1 over root x because of the exponential dying quickly. But it's compatible with solar system data. You could imagine a smoother interpolation, but that would actually run into problems, because if you had a smoother interpolation, then the outer planets, Saturn and Uranus and so on, their orbits would go out of whack in a noticeable way. You could also work with an absolutely abrupt interpolating function, which just changes from 1 to 1 over root x, but that seems unphysical. But that's also not ruled out by data. Okay, so just to get some intuition about this, let's look at a point mass. So the Newtonian field of a point mass, which might well be the sun, goes like 1 over r squared, and it points inward. And then if you work out the MOND field, in this case, the pristine field and the quasi-linear field are the same, because it's a radial field which is curl-free. So you don't have to go to any bother to calculate the curl-free part. And you can rewrite the argument of the interpolating function as in this form. There's something called the MOND radius, which is a characteristic scale of the point mass. That squared divided by the distance squared. This is basically g over a naught, the Newtonian acceleration over a naught, rewritten in this way. Okay, so the interesting thing for us is, well, first of all, I should say that because of this 1 over square root of x, when r is small compared to the MOND radius, then you just get the Newtonian field, the 1 over r squared field. But when r is large compared to the MOND radius, you get a 1 over r behavior in the gravitational field. It falls off really slowly. And that's where the flat rotation curves come from. The interesting thing for us when we started thinking about the solar system is to work out what this number, the MOND radius, would be for the sun. And I guess other people have thought about this before, but for us, it was really quite exciting when we put in the numbers. We weren't familiar with the literature at that time. And what we found is it's 7,000 astronomical units. So that's not very far outside the Kuiper belt. And so one might expect the Kuiper belt could be a sensitive probe of MOND physics after all. Even though this theory was developed to operate on the galactic scale, it could have consequences in the solar system. Okay, so now let's think about what effect what would change if you work with MOND gravity in the Kuiper belt. And it turns out that we have to think about the galactic field as well as the field of the sun. Those turn out to be the most important influences in the Kuiper belt. So this might sound a little bit crazy in connection with Newtonian gravity to be talking about the galactic field, because the field of the galaxy in the solar system is so small that it's essentially constant, the field of the galaxy. If you have a uniform field, of course, all the solar system objects accelerate uniformly in response to it. So it produces no relative motion of solar system bodies. Of course, you might say the galactic field is not exactly uniform. There must be some variations. And that's true. And those are called galactic tidal effects. But you can show that those are negligible on the scale of the Kuiper belt. They do matter on the scale of the Oort cloud, which kicks in at hundreds of thousands of astronomical units, but they're not relevant for the Kuiper belt in Newtonian gravity. Okay, so that's the Newtonian field of the galaxy plus the sun. But what happens in MOND? Well, in MOND, it's basically a very nonlinear theory. So the presence of the galactic field and the sun's field interact with each other nonlinearly. You don't have a principle of superposition anymore. So what you can do is you can write down the resulting solution to the MOND equations in this form. There's the field of the sun, plus there's the constant value towards which the field will asymptote. And then there's everything else. And you can figure out what this GQ, what the MOND field is, starting from the Newtonian field by using the recipe I described. As you remember from the recipe, if you know the Newtonian field due to a mass distribution, then you're on your way to calculating GQ, the MOND field. In case, so we decompose the field in this form: Newtonian field of the sun plus some asymptotic constant galactic field, and then everything else. And this everything else is what we call is in this business, it's called the external field effect. Because this wouldn't be present in Newtonian gravity because there's just superposition in a linear theory. So you get this extra field GA in MOND, and it's the consequences of GA that we want to work out. And I should say over here that this external field effect also happens in galaxies, of course, and the galactic version, there's some evidence for that, which is found in work by my colleagues, semimajor and his collaborators. But we want to stick to the solar system. So one way you could think about GA is you could go ahead and compute its divergence. And that would give you the equivalent amount of dark matter you would need to be producing this effect. Now, of course, if you believe in MOND, this matter isn't there, but it gives you some intuition to work out what the equivalent Newtonian mass distribution would have to be to produce this anomalous field GA. And this mass density is called the phantom mass. It's not a term we invented. It's due to Milgram, but it gave us our Star Wars reference for the title. So that's the phantom mass. And actually, operationally, the way you do the calculations, you start with the Newtonian field, and the first thing you do is you calculate the phantom mass, and then you solve Poisson's equation to get this anomalous field GA. So I'm going to show you what the phantom mass distribution looks like. If you start from the field of the sun, Newtonian field of the sun and the Newtonian field of the galaxy, it turns out that the phantom mass is then distributed as a shell. It's an anisotropic shell centered above the sun. And most of this phantom mass, which is of order the same mass as the sun actually, but it's out there, it's about the MOND radius, as you can see in this plot, in this heat map. So here it's cylindrically symmetric. It's got rotational symmetry about the axis, about the direction to the center of the galaxy. The line passing through the sun to the center of the galaxy, that's our z-axis. And the mass density, the phantom mass density is rotationally symmetric about that. And you can also see there's this weird feature on the z-axis at the MOND radius, but that's not too important. So I won't say much about that. But the important thing is that there's this sort of shell out there. And the inner solar system is really tiny on the scale of this plot. I should probably draw a tiny circle showing Neptune's orbit, but you might not be able to see it. Okay, so the anomalous field is whatever field would be produced in the inner solar system due to this stuff out there. And you can work out what that field is by using a multipole expansion. So in electrostatics, we're used to the following situation. You have some charges close to the origin, and you're trying to figure out the field far away. That's what you use the multipole expansion for. But this is kind of the complementary situation where your charges are in a shell out there, and you're in the hollow, empty interior. But it turns out you can use a kind of multipole-like expansion to figure out the field inside the hollow as well. And this is what it looks like. The dominant multipole moment is the quadrupole. You can actually prove, and there's a nice proof of that the dipole has to vanish for the phantom mass. So the quadrupole is the dominant thing. And the quadrupolar field basically has to look like on dimensional grounds. It's going to depend on the mass scale of the phantom mass, which is of order the solar mass. It's going to depend on Newton's constant. And then for dimensional reasons, I mean, just because it's quadrupolar, it's got to go like r squared in the Legendre polynomial. And then to have the right units, it's got to go like the size scale cubed. And then there's going to be some numerical factor, which we can work out by actually computing the mass and doing a numerical integration. The mass distribution. Mass distribution we can get in analytic form, but then we have to do the integral of the quadrupole moment numerically. It comes out to be of order, well, maybe it's 0.1, but it depends on the interpolating function you use, this numerical factor. And so it can vary a little bit by an order of magnitude. So we have a bit of wiggle room about what this factor f is. But in any case, the important thing is that you get a quadrupolar field. And here's where we get a sort of second clue that MOND might actually be relevant to the Kuiper belt. Because let's think about Planet 9. It's really very much the same thing. Planet 9 is at 500 astronomical units. So it's outside of the solar system, and it's outside of the Kuiper belt objects that we're looking at, which are 30, 50 to a couple of hundred astronomical units in the semimajor axis. So the field of Planet 9 is also going to look like quadrupole. Of course, it's highly time dependent, but if you're interested in the long-term dynamics, what Planet 9 does in the long term to the Kuiper belt objects, you can treat Planet 9 as though it were you sort of distribute the mass of Planet 9 all along its elliptical orbit, putting down more mass where it spends more time and less where it moves quickly. This is actually very respectable in solar system dynamics. It's called the secular. It's called Gaussian averaging, and it's a key ingredient of what's called the secular approximation. So you should think of Planet 9 as a kind of elliptical distribution of mass, and it also produces a quadrupolar field. And you can go ahead and estimate what the quadrupoles are. So in this case, the mass scale is much less than for the phantom mass, but the size scale is also much less. And when you put in the numbers, it turns out that to order of magnitude, the quadrupole of Planet 9 and the quadrupole of the phantom mass are the same. So it's the same order of magnitude. And so indeed, it could be that MOND is an alternative explanation. Okay, so let me just say one more slightly technical thing for people who like technical details. Well, I've already said this. I should have waited for the slide because it would have been clearer. The mass of the planet is assumed to be distributed along its orbit. And if you look at any arc of the orbit, the amount of mass that our arc contains is proportional to the time spent on that orbit, on that arc. So you can use Kepler's anomaly equation to get a really nice analytic formula for what the mass is along any mass densities as you walk along the orbit. And then you can calculate the multiple moments nicely. Okay, so that was just a little technical detail. Let me pause here for a second and ask if there are any questions.
So let me just make sure I understand. So Planet 9, I guess that explanation has something like 3 free parameters basically, because four free parameters, because you kind of decide on the mass and the position, the radial position and the angular position of the epicenter.
Yeah.
And
actually, I would say they have 5 free parameters because they have the size and shape of the orbit. And then they also have the orientation of the orbit, which is completely free.
Oh, the eccentricity, right.
Well, the eccentricity, but also the orientation of the orbit. So the eccentricity determines the shape. The semimajor axis determines the size. And then you can reorient it any way you like. So they have five parameters.
Where by comparison, you're saying if when you guys take the MOND acceleration given by galaxy data, if you take that as a given, then you're saying with no free parameters, you get roughly the same quadrupole. Right.
And I should say they have one more parameter, which is the mass of the planet. Also, is completely up to them. Yeah. And we have to get the quadrupole, they just put in two parameters, which is the mass of the planet and the size of the orbit. those orientation things I was talking about are, are also relevant. I mean, they would lead to which direction the alignment will be in, and so on. Okay, but just to get the order of magnitude of the effect, yeah, they have two parameters, and we have none, but we land essentially there.
Mm-hmm.
So that was, but actually great. So I'm glad you asked this question. There's also an important difference though, which is, the planet 9 quadrupole is, there's a sign difference in the quadrupole. The sign of the quadrupole is different for us. Theirs is a kind of oblate distribution because it's, whereas ours is more prolate. So I guess the simplest kind of quadrupole you could think of, mass quadrupole you could think of, is like a circle, the field that it produces near the origin. That would be an oblate quadrupolar field. And a prolate one would be if you had 2-point masses on the z-axis, very far away, and then you were asking what kind of field did they produce near the origin. That's a prolate field. And the MOND field is prolate, it turns out. Why it's prolate is not terribly clear, but when you just go through the recipe, you calculate the phantom mass density, that's what it turns out to be. Okay, so I guess I'm going to press on then. So now that we know what kind of field MOND produces, we need to ask what effect will that have on Kuiper belt objects. And so here we have to educate ourselves in this beautiful 19th century subject of solar system dynamics, which as physicists we knew nothing about, but it was really fun to learn. And also it had a side benefit that when the movie Don't Look Up came out, we could follow the jargon that that Leonardo DiCaprio and his students were spouting in the opening scene when they were working at the orbit. So that was nice as well, nice timing for us. Okay, so the basic, to give you a quick crash course in solar system dynamics, the basic physical idea is that under the action of the sun alone, the Kuiper belt object would pursue a Keplerian ellipse. With these orbital elements, these 5 orbital elements that I just referred to. There's a 6th element, that's the squiggly CK, that tells you where on the orbit you are. But here we're going to focus more on just what are the orbits, not where the object is. Because if you're interested in the very long term, maybe you don't care about where it is on the orbit. So the point is that under the action of planet 9 or MOND, these ellipses should evolve slowly. That's the basic physical idea. If it was just the sun, they'd stay put, but MOND or planet 9 changed the ellipses and hopefully position them in the way that they're seen. So how do you work out the evolution of the orbits of these ellipses, of the orbital parameters? It turns out that in solar system dynamics, there's this formulation of dynamics which was invented by a whole bunch of people, but again, Lagrange manages to get his name attached to it, so they call it Lagrange's equations. But you work directly with the orbital elements as your dynamical variables. And I should point out, this is very different from what we're used to doing in physics, because in Lagrangian mechanics, what you do is you work with the coordinates and then the rates of change of those coordinates. Those are your basic dynamical variables. But clearly these orbital elements that I was talking about, they're not the rates of change of each other. They don't have that kind of relationship, nor do they come nicely paired together as conjugate coordinates and conjugate momenta, like in Hamiltonian mechanics. So if you work directly with these orbital elements as your dynamical variables, you really aren't doing Lagrangian or Hamiltonian mechanics. You are just doing this really customized mechanics that was invented for the purpose. I should say that they are dynamical variables in the sense that if you tell me what all the orbital elements are, I can work out the positions and velocities and the positions and momenta. So there's a dictionary between those variables. And the cool thing is that you can just write down equations directly that describe how these guys change. That's the idea in a sense. And these equations are quite ugly, but we're going to use the secular approximation to those equations, which is useful for long-time behavior. What happens in the secular approximation is that the major axis doesn't change. And also where you are on the orbit doesn't matter because you're computing long-time dynamics. You just average over the position. And so that's helpful too. So the dynamics is generated by something called the disturbing function, which is analogous to the Hamiltonian here. It's just, if you're trying to work out the effect of MOND on the Kuiper belt object, it's the potential energy of the Kuiper belt object in the gravitational field of MOND. or in the orbit average field of planet 9, if you're working out the dynamics due to planet 9. That's what that quantity is physically. Now, this thing can be quite difficult to work out. It can't be worked out exactly. You want to know what this potential energy is for two ellipses in some arbitrary orientation relative to each other, or of our or of this Kuiper ellipse in the field of MOND, which we are approximating as quadrupole, but it's actually more complicated. So to work it out exactly is not possible, but you can use a multipole expansion either for planet 9's field or for the MOND field. And then you can compute the potential energy order by order. And that is something we found we could do very efficiently. And interestingly, this doesn't seem to be in the literature, because most of the literature is concerned, they assume small eccentricity or small inclination of the orbits, a small range of inclinations of the orbits and so on. And usually you get away with it, but here we need exact expressions. And we found that we have exact expressions. And so I've just put down the exact expression over here, but you don't have to look at it. I just couldn't resist gloating. At some point, we will try to write a paper, though, on orbital dynamics, explaining our process, which allows you to do these things exactly. But the one thing I do want you to notice is that this disturbing function doesn't depend on one of the Euler angles. So you start off with the ellipse in a standard orientation, and the Euler angles are the usual thing. You twist it about one axis, and then another axis, and then twist it again around the same axis. And you would expect, because there's a kind of rotational symmetry about the direction to the center of the galaxy, you would expect that the last twist will not change the potential energy. And so you see the absence of a dependence on capital omega over here. And that is worth noting. It's due to rotational invariance. Okay, so again, I kind of jumped the gun here. This is the slide in which I was going to explain the Euler angles. Sorry, I don't seem to have a picture. I don't know what happened with that. But basically, the origin is located at the sun. The galactic center is along the positive z-axis. So I start with my KBO ellipse in the xy plane. I think you can picture that. It's in the xy plane. And the perihelion, the point of closest approach to the sun, is along the positive x-axis. And then the orientation omega corresponds to what you would get if you took this ellipse and you twisted it about the z-axis, and then about the x-axis, and then again about the z-axis. That is what that orientation corresponds to. You can also, it's also worth thinking about two vectors. There's the epsidal vector. Actually, let me come back to this later on. I'm pretty sure it'll be more relevant later on. Okay, so I've just explained to you what I mean by those orientation variables. And now I want to talk about working out the dynamics. So we have four variables because the semi-major axis doesn't change, and we don't care about where we are along the orbit. So the four variables are the three Euler angles and the eccentricity. Those are the orbital parameters that might evolve. But it turns out we have two conservation laws, because this disturbing function itself is conserved. It's just the potential energy of the orbit in the MOND field. And it turns out that the angular momentum along the symmetry axis is also conserved. And it's basically given by this expression over here in scaled form. So that means we have an integrable model. We have 4 degrees of freedom, or 4 coordinates, and we have 2 conservation laws. So what you can do is the disturbing function R depends on 3 of the parameters, the inclination, the little omega, and the eccentricity. But you can get rid of the inclination. You can eliminate that in favor of the conserved quantity H. And so then you get R effective, an effective action, which just depends on 2 of the parameters. And so you could plot that in the E squared versus omega plane. What I've plotted over here is contours of constant disturbing function. And so the KBO, its orbit is just going to move along these contours. The interesting thing is that the Z component of the angular momentum determines the nature of this plot. When the angular momentum is large along the, which means that the orbit is perpendicular to this symmetry axis, then these contours are just wavy lines running across the plot. And so, so the KBO, it just precesses uniformly in omega, and its eccentricity sort of bobs up and down. But if H is small, then you get these fixed points. You get these domes within which the orbits are circles around the fixed points, or the circulate around the fixed points, and then you get these wavy lines outside of the domes. So that's kind of completely different behavior. If you were at a fixed point, this parameter omega is actually fixed in time, and the eccentricity is also fixed. Or you might just undergo small variations around that fixed point. That's what the dynamics will be like. And that's interesting, that because the other thing I should point out, I should also say that there's the other Euler angle, big omega. You might be wondering what that does. That's all latched to these two variables. So once you know what these guys are doing, it turns out big omega just precesses uniformly, no matter whether you're at a fixed point or in the wavy portion of the phase space. And the inclination is completely latched to the eccentricity. So it does whatever the eccentricity does. If the eccentricity is bobbing a little bit, the inclination is bobbing a little bit too. Okay, so now you have a picture of what the dynamics are when we only take MOND into account. But of course, you realize that there will be perturbations due to the gas giants, due to the fact that the Earth is moving slowly around the galaxy, and so forth. And so, in fact, this dynamics, you expect it to undergo the usual kind of KAM transition to chaos. And you expect most of it will be a chaotic sea, but there may be some island of stability around each of these fixed points. One other thing I should point out, and I won't dwell on it too much because I should also be getting to my punchline, is that the fixed point on the right is more stable than the one on the left when you take the octupole term into account. And so that's the one that I think will survive once you turn on all the perturbations. So that's where we predict a family of KBOs should lie around the fixed point to the right. Okay, so the location of the fixed point can be worked out. It depends on H. And I guess I've said all of these other things already about the additional perturbations, about there being a chaotic flow, except near the stable fixed point. Yeah, okay, so we can move on. So that's our key prediction. We expect KBOs close to that fixed point. So what happens if you're sitting right at that fixed point and you have very small h? Well, you can work out then that the inclination I is pi over 2. And since omega is minus pi over 2 or 3 pi over 2, whatever you want to call it, you can work out that the epsidal vector, if you just think about what the epsidal vector is, so that's the vector from the sun to the perihelion. If you start on the standard orientation of the orbit, it's along the x-axis. But then if you rotate it by 90 degrees and then minus 90 degrees, it ends up pointing along the negative z-axis. In other words, it starts pointing opposite to the direction of galactic center. Now, if you're not right at this fixed point, it won't be pointing directly away from galactic center, it'll be pointing, it'll make not a 180-degree angle with the direction to galactic center, but it'll make a large angle anyway. That's what you'd expect. So that's the takeaway over here. Our key prediction is that these epsidal vectors should point away from galactic center. And so now comes the moment of truth. Do they? So it turns out there's this thing called the Minor Planet Database, which is also featured in Don't Look Up. And it's real, and you can go there. It's a really nice example of open science, searchable. We found these 6 Sedna family objects. And then we go ahead and we plot up their orbits. And they're lined up, of course, just like you see in the Planet 9 review article. These orbits are nicely lined up. But the additional feature I want to point out is that they are lined up with the direction to galactic center, which, previously you would have been crazy to plot that on the same plot. But in MOND gravity, you've got to do that. And so this was really dramatic and kind of remarkable for us to find that it's lined up so nicely. I should also say that there's an intuitive explanation. You can see that the orbits, if you imagine distributing the mass around the orbit in the way I've been describing, you can see that the aphelion, when it's far from the sun, that's the heavy part of the orbit because this Kuiper belt object is moving slowly. And you can see they're all hanging with the heavy ends towards galactic center. They're being pulled towards the center of the galaxy. So the nature of this alignment is quite intuitive as well. And there's so many things that could have gone wrong. They might have been lined up, but not with the galactic center, or they could have been pointing the wrong way. And these are all things that we didn't know how it was going to turn out until we made the plots. And it turned out that the heavy end was lined up exactly as you'd expect. Okay, but I should stop talking about our feelings and try to be more quantitative about this. So you can characterize the alignment by calculating the epsidal unit vector dotted with the galactic center unit vector. And if these epsidal vectors were perfectly random vectors, you would expect this thing to be 0 on average. And you could work out what the typical deviation from 0 would be also. And the value we actually measure, it's about minus 0.7. That's 3 sigma away from being purely random. Or you could just ask, what are the odds that you would get these 6 guys to be pointing in the way that they are if AK was purely random? And the odds of them being all within a certain cone that they lie within, that's 1 in 500. So it's not quite the 5 sigma gold standard, but it's certainly, certainly intriguing. There's another thing which I guess I'm just looking at the clock and realizing I won't say very much about this, but it turns out that you can also plot up the values of the fixed points for these 6 objects, the E squared and omega values for that fixed point using the formula I had shown earlier. That's what the red dots are. And then you can plot the actual eccentricities and omega values that are measured in the minor planet database for these objects. And you see that they're clustered around the fixed point. And that's sort of consistent with that picture also. We don't expect them to be sitting right at the fixed point, but we expect them to be within the basin of stability of that fixed point. And they kind of are. So that's nice too. And I mean, I should say, of course, it's obvious that in future work, we should quantify how big the basin of stability is and see how good the agreement is. And that's work in progress. It will require us to do simulations, which are ongoing. Okay, so to really make this a slam dunk, obviously we need a much larger sample of Sedna family objects. And we also need to carry out dynamical simulations to sharpen the MOND predictions. And the good news is that there are all these surveys that are ongoing or coming online very soon. And all of them are capable of discovering hundreds of these objects. And so we could have a very large sample very soon. And I think it's particularly fitting that a telescope named after Vera Rubin might help. It's going to do a solar system survey, but it might actually help illuminate the questions that her work originally raised about galaxy rotation. And so really there's 3 ways this could fall out. It could turn out that the signal will, there are only 6 or 14, depending on how you count objects right now. And you could argue that there are observational biases. The signal could go away. It could be small number statistics. Or, if they find planet 9, if they really see it, it's going to be kind of hard to argue with that. That could happen too. Or it could be that when hundreds of objects are found and planet 9 is not, the evidence for MOND will slowly strengthen. It's another question which maybe we can take up in the Q&A, whether that would be a slam dunk for MOND. I don't think it would. We would need more things, but it would certainly be a really compelling and interesting discovery, I think. And certainly, if you look at the history of gravitational anomalies in the solar system, they've often been spurious, but they've also led to the discovery of a planet, and they've also led to the discovery of a modified theory of gravity. So all outcomes have happened in the past, and any of them could happen in the future. But I think definitely one takeaway is that the Kuiper belt is not just of interest to planetary scientists. It is a laboratory for studying fundamental physics. All right, so I'm going to stop here, and thanks for your attention.
All right, thanks. Let's thank Harsh for that great talk. Maybe I'll start with a question. So what are the prospects for getting a lot more of these Kuiper belt objects if you wanted to?
Sure. So here we are. So there's all these surveys, that are on, dark energy surveys ongoing, and this exoplanet survey is also ongoing, and all of them do see these objects. Like I think they've reported dozens over the past few years, each of them. And then there's this OSOS, which is actually dedicated to looking for Kuiper belt objects. So they tend to discover them, each time they do a data dump, they've discovered like hundreds of them. But they're not all in the Sedna family. Yeah. So that's the thing. So we do expect that the yield will be of Sedna family will be lower, but things like Vera Rubin, CMBS4, and also Gaia are discovering these also. I mean, Gaia is also discovering them at more or less the same clip as Dark Energy Survey, but I think Vera Rubin and CMBS4 could potentially dump huge numbers.
And so the ones that are being discovered at a higher rate, the problem is they come too close to the center of the solar system, and
Yeah,
they're too.
yeah. So I think the most recent OSOS, or however you say it, I'm not in the field, so I've never actually heard anyone say it out loud. They had something like, I don't know, 6, 7, 800 objects, but the ones that were Sedna family were only 5 or 6.
And you really can't use them, or the signal is there's no signal
No, so those 5 or 6 we could use, and we did. Sorry, I don't have this.
The several hundred. You expect there to be no signal, or it's just going to be harder to.
It's going to be harder to work out because they're perturbed not just by MOND or Planet 9, but they're also strongly perturbed by the inner solar system. So yeah, there's no signal. I mean, basically, they get knocked out of these stable orbits, or these orbits are not stable for them because they're in the inner solar system. But we could certainly use the handful of additional objects that have been discovered. We took a very conservative position. So the big review on Planet 9 was written in 2019, and at that point there were 14 objects in this family, but 6 had stable orbits, and the other 8 were more iffy. But we could plot up those 2, and those line up pretty well too. I'm sorry, I don't have those plots, but they basically look the same. They cluster in phase space, they line up equally well. I just feel like maybe it's a little too aggressive salesmanship to include them. It does sound nice to say 14, but if I know that they're actually unstable, then I shouldn't be using them. And then there's 6 more that have shown up in the database since 2019 that we found that basically satisfy the criterion of being far out and so on. But still, we haven't done orbit dynamics on them, so again, I'm a little hesitant to include them. But maybe we have 12 objects, and once we've got our orbit dynamics programs working, we'll be able to vet them.
Would another way? I mean, I remember that there was this. There was a paper a few years ago by Witten suggesting that maybe instead of Planet 9, there's actually a Planet 9 mass black hole lurking in the outer solar system, and there was this suggestion that you could find it by sending small satellites, send back radar signals, and timing the radar signals very accurately. Is it something where if you wanted to get, I'm just trying to think, if you wanted to get somehow the quickest way to get a much more accurate measurement of where this extra gravitational field is pointing, could you
yes
maybe do that?
Yes, no, that's a great idea, and actually, we have work in progress on that, and in fact, we started that work first, and somehow it's not complete yet. But MOND and Planet 9 or a black hole. I mean, a black hole or Planet 9 are not that easy to distinguish because they just point masses, but they're distinguishable from MOND. Using breakthroughs, using these star shots that people have talked about, that Witten was talking about.
Yeah. So you have some very particular prediction for the modification of the gravitational field. So I guess you can see the satellite just move in a different.
Exactly, it's quadrupole and it's lined up with the galaxy, and so it's pretty unambiguous. And I agree. So that goes to the point I was making, that at what point are people going to start believing that maybe there's something to MOND? I think we'll need several lines of evidence. We do need, we would need star shots, I think, as well as more data on the Kuiper belt.
Jesse? Oh, I think you're muted.
Wrong button. Thanks for the talk. So I haven't been following this closely, but I know there's some discussion at the Planet 9 literature about looking at selection effects, which you kind of touched on, in terms of even to try and propagate some uncertainty into how much that angular clustering is actually detected. Have you thought about ways to propagate that uncertainty to what's this telling you about your findings?
So I guess I'm afraid yes, I think that's a very important question, and we are starting to think about it, but I'm afraid we don't have anything useful to say yet. It's something we're worried about. So I can only tell you, I can only paraphrase what other people are saying. As you said, there are people who say that there are strong selection effects and the alignment is entirely due to that. And then there are people who say no. And we've looked at enough different surveys. And so, yeah, I mean, it's obviously imperative for us to figure out which of them is right. But it's also the case that I don't really care that much about it. I mean, I think the thing that the thing that Latham just suggested is perhaps strikes me as a more pressing project, because I think eventually we'll get these giant surveys like Vera Rubin, which don't have any observational biases at all, and well, no, that's no statement, but less biased than the existing surveys. So this will become less of a concern, and I'd just rather wait till we have more data points rather than nitpick about these 6, whether they're biased or not.
Any other questions? Okay, if not, well, that was a great talk. Harsh, thank you so much. Very interesting result. I look forward to you guys posting it. And yeah, thanks again for talking to us.
Will do. I'll make sure to shoot you an email when we finally get around to that, which I hope will be quite soon. Yeah. All right. Well, thanks for having me. It was fun.